ITC Colloquium of the fall, and today we have Kartheik Iyer, who is visiting us from New York, where he first was a Hubble Fellow at Columbia and then moved to CCA, where he is now a Flatiron Research Fellow. And in the fall 2026, he will move to Hawaii as a faculty fellow. Right, so I hope you won't miss New England weather there.
It will be so hard living in the tropics.
You should visit us more often. Yeah, and apart from work that Kartheik will tell us about today, he also works on applying statistical methods to and AI for the search of literature, and essentially trying to help us handle all this immense amount of literature coming up every day on the archive. So if you also feel overwhelmed, please talk to Kartheik.
I'll talk about that advanced too.
Great, awesome. So, and with that, please take it away.
Thank you so much for having me here. It is an absolute pleasure to be back and to talk to you about some of the stuff that we have been doing, looking at variability in galaxy star formation and how that ties to feedback. A lot of this stuff actually starts here back in 2018 when I was visiting and working with Sandra Takela, who was a postdoc back then, and talking to Lars and folks here. So this is sort of coming back in a sense. Okay, so yeah, a lot of this work is possible because of my incredible collaborators. So huge thanks to them for helping me, with all of this. I don't think I need to tell anyone here that galaxies are complex systems, but I will anyway, because that's a good start. And it's a common motivator for why all of us tend to look at it in some way, shape, aspect, or form. Galaxies made of a bunch of different components like gas, dark matter, and stars tend to experience a variety of different physical processes that change and regulate the way they're able to form stars and the way they look over time and so forth. And the result of this is that when we even look in our local backyard and go all the way out to high redshift with telescopes like JWST, we see galaxies that look very different from each other, right? So these galaxies all have the same building blocks, more or less, and they all have the same set of physical processes that act on them, more or less. But they end up looking very different. And so the question that I tend to focus on is what are the physical mechanisms that are driving this diversity that we see in galaxy populations, in galaxy properties, and to try to then see how that is linked to their formation histories. How does this tie to their past? Back in 2020, we tried to compile like a set of all the physical processes that act on galaxies on different timescales. You could make a similar plot showing how these processes act on spatial scales as well. But the interesting part here is that these timescales span many orders of magnitude, and they often tend to be interacting. So it's not like you can talk about any one of these processes in isolation. You can't study them without considering the effects of the other things. So we go to simulations. We say, okay, let's put these processes in. Let's try to do, as realistic as possible a job. But then in projects like Agora, where we have essentially the same initial conditions, but different prescriptions for physical processes, you end up getting galaxies that look quite different from each other. So then the question becomes, okay, so even slightly tweaking these processes, what they are, what kind of effect they have on galaxy properties, tends to produce very different looking galaxies, very different formation histories. So we need observational constraints to limit these things, to say, like, what's the correct ballpark that we need to find ourselves in? And people do this kind of observational constraints in many different ways, ranging from, population level things like looking at luminosity functions or mass functions and so on, where you just take all the galaxies that you observe, weight them by your volume, and then look at their distribution as a function of some property. Or you look at specific things like massive clusters of galaxies or dwarf galaxies that tend to give you constraints on specific processes. And What I'm trying to go for today is something that sort of falls in between these two things. I'm going to pitch to you that the way a galaxy forms stars over time tends to contain imprints of these different physical processes and provides a good workbench that we can test different theories on. So I'm going to break down that first question that I said into two sub-questions. One is, how do we take our observations and convert that into some information of the past lives of galaxies? And then the second question is, okay, if we have these observational star formation histories, how can I then use them to get constraints on physics in some way? I am not going to talk too much about number one, but please feel free to ask me if that's something that you're interested in. So the basis for number one comes through this thing called spectral energy distribution, or SED fitting. And this is work done with, as part of my PhD and with a bunch of collaborators and students. Similar work over here would be prospector that Ben and Joel and folks have worked extensively on. But spectral modeling tools can be used to constrain star formation histories, is the overall claim. And so the reason we are able to do this is because galaxies tend to look very different at different wavelengths. And the reason that happens is because galaxies get contributions to their overall emission from a bunch of different sources, ranging from stellar light, from stellar populations of many different ages, to nebular emission, to emission from active galactic nuclei and dust. And if you look at galaxies at different wavelengths, you're just seeing different weighted components of this that depend also on the galaxy's properties. So what we do is we use a bunch of telescopes to image galaxies or take spectroscopy of galaxies across as wide a wavelength baseline as possible, or with as much resolution as we can if we care about things like emission lines. And we try to turn that into constraints on physical properties. So if we go back here and we try to isolate just the stellar continuum, that, assuming we can get to it, tells you something about the composition of the different stellar populations that make up this galaxy, because stars of different ages tend to have different spectra, and what you're seeing is all of them added up into something called an integrated SED. So if you can disentangle this in some smart way, then you can get a breakdown of how many young stars or old stars there are in a given galaxy, and therefore something about the stellar populations. So the way I describe a galaxy's star formation history is by saying that my free parameters, because I don't want to assume that a galaxy's history has some functional form, my free parameters are the times at which it formed different fractions of its total mass. So T25 would be when it formed 1/4 of its mass, T50 when it formed 1/2 of its mass, and so on. And these are the numbers that I then try to back out of the observations. And so if I get this, I'm getting some constraint on the shape of the history. This is all I'll say about it today, but if you're interested in this, you can go read up more at the bit.ly link, or just install it and try playing around with it. The upshot of this is that we can now apply this to large ensembles of observations that span a range in things like redshift or stellar mass. And so here I'm showing what happens when you apply dense spaces to the 5 candles fields that were seen with the Hubble Space Telescope. And you can see that you see this like neat transition from low mass galaxies at high redshift being mostly rising, they're forming most of their mass when we see them, to massive galaxies at low redshift that tend to have formed the bulk of their stars and are now quiescent. JWST, when it came on, saw nearly 1 million galaxies in its first year alone, spanning almost a square degree on the sky across a bunch of different surveys. And as part of a few surveys, I got to play with some of this data, and this fully blew my mind, because for the first time in my life, I was seeing observations that were going down to nanojanskis, which was orders of magnitude deeper than anything that I had worked with before. So it was a pure pleasure and a privilege to be able to play with these things. But so the nice thing is now you can sort of extend this out to much lower masses and much higher redshifts than we were able to do with Hubble. So for reference, the Hubble plot that I showed you just before was that tiny bit of parameter space. And so now you were able to go down to much earlier epochs, and you can sort of see the same galaxy or the same population of galaxies as they assemble their stars over time. So you can see things that look like extreme starbursts. These are these like very low mass, very high redshift galaxies. Well, not very high redshift by JWST standards, because that's gone to like redshift 14 at this point, but pretty high redshift when the universe was a bit over 1 billion years old. And then you can sort of see these as you're sort of tracing along this trajectory. So you can see it going from like these low mass starbursts to star-forming galaxies to things at cosmic noon to massive cosmic known galaxies that have now settled into this sort of steady state to very high redshift galaxies that have fully ceased to form active stars on average. Again, this is the median and the 1 sigma distribution for like all the galaxies that fall in that bin. So the thing is, we have these observational constraints that come from these modern high signal to noise surveys. And I write a lot of proposals where I say, if we get these observational constraints, we can constrain something about galaxy feedback, and we can put all these like new things to work in terms of learning something about physics. And so that's what I want to talk about today. So how do we tie these formation histories to the underlying physical processes at play? The basics of this is something that I think everyone here already knows, but I'm going to repeat it for being pedantic. We get observations across a range of wavelengths, convert that to information about stellar populations, and then we have either pure theory, some sort of analytical model that has a simplified notion of how galaxies evolve, or we have these full physical cosmological simulations with all the physics that we can think of that we have put in. And we want to connect all of these. So what we need is some sort of intermediate space or intermediate baseline that you can get to with both the observations and the simulations. And so this is where I'm pitching star formation histories as my candidate for what you should use to try to do this kind of physical comparison. So what I'm trying to do is building this sort of temporal picture of how galaxies are growing over time and quenching over time, and how their star formation changes as a result of physics. People do the same thing in the spatial regime, where you essentially talk about characteristic length scales or physical scales of distance that different processes act on. And so this is a complementary approach to that. It's not meant to be a replacement. It's both like you can get independent constraints. And for sake of simplicity in this talk, I'm going to just divide this into short, intermediate, and long ranges of effective timescales instead of talking about any individual physical process. And so you now have this phase space of time or time scale on the x-axis, going from less than 1 million years to many tens of gigayears, and number of galaxies that you would need to get some kind of constraint on the y-axis. So dense basis that I talked about a while back sort of sits in this regime, where it tends to focus mostly on long-ish timescales and can scale to basically any number of galaxies as long as you have enough computation to throw at it. And so this can give you, like, that's the regime in which dense basis allows you to get observational constraints. At the other side of this is looking at really short timescales. So this is looking at emission from really massive stars, usually, that tend to have very short lifetimes, and seeing if you can get any constraints by looking at 2 different indicators of how bursty, which is the term that people often use, star formation is. And so this is possible because, like, on these short time scales, things like H alpha and UV tend to trace star formation quite closely, but not identically. And so if you make distributions of a bunch of observations where you have H alpha and UV measurements, you can compare those distributions to say whether on average star formation rates are rising, flat, or falling in like the recent time. And then you can turn that into whether most galaxies tend to be rising also, so they don't have much diversity in their population, or whether there's a huge spread in like some galaxies are rising, some are falling, and so on. And so there's been a bunch of studies that look at this both on a integrated scale, on galaxy subsamples that are classified as things like interacting versus isolated, or in spatially resolved ways where you can sort of isolate clumps and look at whether their behavior is different from their parent populations. And so this is something that's a very active field of study. People really care about burstiness because they think that constraining what's happening on these short timescales gives you a lot of insight about how star formation happens locally. So that sort of sits on the extreme end of like how short we tend to go. And I want to talk a bit about things that sort of bridge this gap. So this is stuff that actually started here. So working actually with two former CFA people, so Sandra Takala and later with Josh Spiegel, we were trying to first see how the burstiness or the amount of star formation variability changes as a function of time scale when you look at many different simulations, and then to try to analytically model this in terms of some kind of physical prescription. So this was from back in the 2020 paper where we were like, oh, let's look at, let's look at how the amount of variability, so that's the power spectral density or PSD, changes as a function of time scale in galaxies in the illustrious TNG simulation as a function of stellar mass. So this is just in bins of stellar mass showing how the PSD changes in slope and normalization. Higher values here mean that things are more bursty, and steeper slopes here mean that the timescales are more unlinked from each other. So you can think of this in terms of like white noise, red noise, pink noise, and so on. And then on the other side, I'm showing basically how the star formation histories look like on average. And then you can take slices of this at different timescales, and then just plot the power on the x-axis on that timescale, and then plot the slope of that power. So how much it talks to timescales that are immediately above and below it. And you can start seeing that there's the increasing size of the dots is increasing stellar mass. So you can see that there's some kind of trend in terms of like, especially the long time scale power tends to increase with increasing mass, and it also tends to become steeper in slope as quenching sets in. So we were like, oh, we can use this to make some kind of projections for what might happen to galaxies as they grow more massive. And then when we look at the other simulations, you're like, okay, so the other simulations might vary a bit, but should roughly follow the same trend, and we can use that to make a model. You end up getting this, which does not have any sort of consensus in their trends with mass, or even in their overall, the part of phase space they span, how they change anything. So I scratched my head for a while about what this means, and came away with two reasonably optimistic conclusions rather than like nothing works, which was that the simulations are very sensitive to the kinds of physics that you're putting in, and that this is a space where we really need observational constraints. So we want to go and get constraints, and we want to figure out why these things are different when we change the physics like this. So this was where the observational constraints part of this came in from. Josh and I built on earlier work by Sandro, John Forbes, and Nevin Kapla to make a way to straightforwardly constrain some aspect of the power spectrum from observations. So the way we did it is this. Star formation histories are bursty. They tend to have variability on many different time scales over time. And you can make analytical models based on these extended regulator frameworks that tend to parameterize how the power spectrum looks like. So basically have a functional form to fit these curves that put in physically motivated effective timescales for things like gas and flow and baryon cycling and so on. And you can then take these and you can put it in something called a Gaussian process, which allows you to sample from these power spectra in a very computationally low-cost way. So you take the power spectrum, you turn it into an autocovariance function, so it's in real space instead of Fourier space, and then you sample. And so you create many such curves, and we put together the simple package that allows you to do this in like a less than 10-line way. And so the nice thing you can do with this is that if you have a base star formation history, something that looks simple and doesn't have any of this extra burstiness, you can now add on burstiness in ways where you're either changing the total amount of burstiness or you're changing the time scale over which star formation is correlated. So this allows you to create these populations of realistic star formation histories that you can then use to forward model into observational space. So you can take each of these histories and you can use something like FSPS, which is also a CFA thing, to model it into observational indicators like emission in the UV or the H alpha emission or even longer timescale things. So you can try to span a range of timescales. And then you can say, okay, if I then train a neural network to take these observations and tell me what the base part of parameter space is that I'm sampling from, given an actual observation. With a single observation like this, where you have like one H alpha measurement, one FUV measurement, and one H delta measurement, you get posteriors that are essentially wide and spanning the whole parameter space and saying, I can't really tell. But then when you start doing this for populations of galaxies, when you go to even as little as 30 galaxies, you start getting pretty reasonable constraints. And those constraints essentially come because now we have histograms. We have distributions of these different observational tracers that trace star formation on different timescales. And you get their covariances. And those covariances really allow you to distinguish between the different regimes of burstiness. So this allows you to get some kind of constraints on the shape and slope of the power spectrum. And this is something that I think Sandro's students are working on applying to JWST observations. You can also take this forward and apply this to see how the power spectrum changes over time using wavelet transforms that Vadim's working on. Or you can even do spatiotemporal power spectra, which is something that I've been looking into but haven't gotten anywhere with. So if you have interest in that, please talk to me. So that's sort of in this intermediate regime. The other part I was doing is seeing if we can make the dense spaces constraints talk to something from the simulations. So here I was looking at suites of simulations. So this is not a single simulation that has one value for different parameters governing feedback, but entire suites. So something like Illustris TNG that I showed earlier, run 1,000 times, varying the strength of supernova feedback, of feedback from active galactic nuclei, and so forth. And then seeing how the star formation history on average can provide a constraint for these parameters. So the basis for this study was that we know that changing cosmology affects how structure forms at early times and therefore should affect how galaxies begin growing and therefore how galaxies end up looking like at redshift 0. And we know that the way feedback from galactic winds and from AGN drives material and heats up material tends to regulate star formation pretty strongly, and also affects things like the structure of baryons in and around the galaxy, and how the galaxy quenches and so forth. So what we were trying to do is there's a bunch of different camel studies that are looking at everything ranging from baryon from the matter power spectrum to Sunyaev-Zeldovich observations. I wanted to look at how the star formation history shape on really long time scales, like the kind we get from dense spaces, are affected by changing feedback. So this data is from the suite called Camels. We used 3 different suites of about 1,000 simulations each, coming from the Illustris TNG, the Simba, and the Astrid galaxy formation models, just so that we can talk about both changing entire physical prescriptions, but also the strength within a physical prescription. I think people here how many people have seen this sort of like things in camels evolve differently kind of plot? because I feel like a fair number would have seen this. But this is just trying to show, to highlight the difference between these models and the fact that they tend to produce maps that look quite varied from each other, especially as you go down to lower redshift. And it's gas temperature, as far as I know. And this is the much less glamorous, but for me, much more informative read the docs page showing the wide range of different galaxy models that are being simulated as part of this CAMELS project. In addition to the 3 that I talked about, now there's also like a full set of 1,000 boxes for Swift Eagle that I want to go and compare these results to at some point in the near future. So the thing that I'm trying to do is, in CAMELS, there's a Latin hypercube. So there's the 6D parameter space that gets simulated with 1,000 different runs that sort of populate the space, that vary the cosmology, 2 parameters controlling galactic winds, and 2 parameters controlling feedback from the AGN. And one would be the fiducial value for these feedback parameters, and they're perturbed in a way where it goes both either a factor of 2 or a factor of 4 lower than the fiducial value, or a factor of 2 or a factor of 4 higher. And what I'm trying to do is draw star formation histories from different parts of the parameter space and see how varying the feedback changes the shape of the history. So the first thing, the way this paper started out was originally like, can we just use the star formation histories as a constraint? Like, can we pass in an ensemble of star formation histories that you might observe from JWST and ask it to give us posteriors in this feedback space? And it seems to be that to some extent you can, although there's significant degeneracies, and some parameters are constrained better than others. So does feedback affect the star formation history? Can you constrain it? Yes. Sort of. Some parameters work really well, and some parameters not so much. This is showing results only for TNG. As you change the size of the sample, you can see that the parameters grow more and less constraining. You get better constraints with larger sample sizes as expected. And you can give in different summary statistics of the star formation history. So you can give it only stellar masses, which is sort of like a coarse sampling of the mass function, or you can give it only shape parameters, or you can give it the star formation history and the short time scale burstiness, and see how your constraints change. Yes?
It won't take too long.
Okay.
Can you tell us what these two, what is AGN1 and what is AGN2?
Yes, so I'm getting.
Going to tell us
Yes, I'm on purpose not talking about what these parameters are.
And you're going to?
Yes. Okay. Yeah, absolutely. And the results also change across the different models. So for example, for Astrid, you're able to constrain AGN2 where you aren't for the other 2. So what are these parameters, right? Yes. Perfect. And the issue is they're different parameters across different simulations. So they're not the same. So in TNG and Astrid, SN1 and SN2 tend to control the amount of energy output as a unit scaled to the star formation rate, or the speed of the galactic winds. And in Simba, it tends to be the mass loading factor and the wind speed. So this is slightly counterintuitive. I mean, these were chosen based on the way star formation is implemented in these models as things that you could easily scale. But there's this relation between E dot, the energy per unit SFR, M dot, and the square of the wind speed. So if you're changing the energy per unit SFR while holding the wind speed constant, that's a different effective result from changing the mass loading factor while holding the wind speed constant. And then the AGN parameters tend to be quite different in the 3 models, depending on how they've implemented AGN and how they've implemented AGN feedback. Again, these were chosen to be as similar as possible, but they're not exactly the same. So this sort of upset the whole project because like we're like, there's no point in getting constraints on these parameters if the parameters don't mean the same thing across the models, especially because then you can't do things like train on one model and test on the other like you would do with cosmology. So we flipped the project. We were like, okay, let's keep that aside for a bit, and let's instead look at, we have this like nice trained normalizing flow that we have used to learn the mapping between this feedback parameter space for each model and how the staff formation histories look. And so if we just walk along trajectories in this parameter space, how does that cause the staff formation history to change? So if I increase the amount of energy that's put out per unit staff formation in these galactic winds, then what does that result in my galaxy looking like? And so this is the summary plot showing how varying each parameter causes changes in the star formation history as you go from lower values to higher values, using the color bar for each of, or the scale for each of these. Again, these are not exactly the same parameters, but in some cases they are, which is a helpful point to get started with. The other thing we can do in this normalizing space is not just walk on these horizontal tracks, but also walk in diagonal lines or basically in any path we want. So that means that we can now start looking at covariances as well. So you can, because earlier I mentioned that all of these physical processes talk to each other, so it's not always, changing one physical process doesn't always have the same effect because it depends on the values for all the other things. So here I'm showing for the Astrid model how changing the wind speed and changing the amount of thermal feedback from AGN feedback actually causes entirely different effects for what happens when you change the wind speed, depending on, or what happens to the AGN feedback depending on the value of the other. If you compose the effects of these two changes linearly, that's the sort of dotted lines that you see in the star formation history. But when you actually use this neural network that we have trained, you see that the net effect is different from what you would expect from just the linear composition. So there are these strong nonlinear regimes for some parameters, not all of them. But this allows you to find that. So coming back to the question of like how the star formation histories are affected by feedback, well, it varies. Changing different parameters does different things, as you'd expect, but in ways that you can start understanding when you look at other state variables of these galaxies. So I'm just going to look at, I'm just going to show two different models. So this is the TNG when you change SN1, which is the energy per unit star formation rate. And this is Astrid when you change SN1, which is energy per unit star formation rate. These effects sort of both go in the same direction, but they're very different in the manifestation of how they change the shape. And so to figure out why this is happening, we started looking into quantities like the mass of the black holes as a function of these feedback parameters, or the amount of baryons in a subhalo as a function of these feedback parameters, because that gives you some kind of a state variable that also traces what happened to this galaxy. And so you can now start pinning these to changes in the star formation history. So if you look at TNG varying supernova 1, you can see that as you increase the energy per unit SFR, this leads to black holes that get starved, and so they don't grow as much. And because they don't grow as much, they don't tend to quench late time star formation as much. So you can see that as you increase the SN1, this leads to lower star formation efficiencies on average, but it also leads to a lack of quenching at late times compared to the fiducial case. And so you can start playing these sort of games looking at how the black holes change. But even then, it doesn't quite explain the differences between the four. So this is just black holes. This is the baryons. So this is looking at whether matter is getting blown out of the subhalo or is stopped from accreting in the first place when you change these feedback parameters. And so here you actually see sometimes flipped relations between SN1 and SN2, where in the earlier case in black holes, it was generally in the same direction. And so this is now telling you two things. In the earlier case, it was telling you whether or not the black holes have stopped from growing. Now this is talking about whether or not the subhalo can hold on to its baryons as you change this feedback. And so when you put those together, you can start getting a bunch of different conclusions for each case. So for SN1, SN2, AGN1, AGN2 as a function of model, plus the two cosmology parameters which are the same in all the models. But this becomes a bit annoying to write a paper about because it would just be a bunch of case studies saying like, okay, so I varied, SN1 in this model and I saw this result, which is really cool to look at but doesn't give me an overall understanding. So we tried a few things. The first thing we tried was to reparameterize things so if we know that there's a relation between E dot, M dot, and wind speed, can we reparameterize it so that we are always varying the same thing? And when we do that, to some extent, we start recovering trends that are consistent across the models, which is as it should work. But then we have a much smaller parameter space that we can do this for. We can't do this with AGN parameters, for example. So the second thing we tried was this really interesting interpretable machine learning approach, where we said that, okay, let's parameterize the star formation histories in some really simple way. So we used a double power law. So there's a power law rise in star formation at early times and a power law fall in star formation at late times, and overall normalization, and then some time at which the history peaks. And so if you change these four parameters, this is how the shape of the star formation history changes. And this is the average star formation history for a bunch of galaxies in a bin, right? So it's not that individual galaxies need to do this, because individual galaxies are much more complex and they can do a lot of things. And we went through this three-step procedure. So the step one I talked about, which is we train a normalizing flow so that we can sample densely all over this parameter space. Then we use something called symbolic regression that I'll talk about to sort of discover a set of equations that tell you how the star formation history changes when you vary feedback. And then the third thing is we try to construct a set of equations by hand that takes this information from the equation discovery step, but tries to generalize it across the three models. So symbolic regression is really cool. Have people here played around with it at all? Okay, a few people. So it's this fun way of saying, normally when I do regression, wait, how am I on time? Okay. Normally when I do regression, I tend to specify some kind of functional form, and I'm regressing for the coefficients of those, either the linear or the nonlinear components of this model. In symbolic regression, you're instead regressing to try to find an equation. So the way it works is there's different implementations of these of symbolic regression algorithms, but the one I used uses a genetic algorithm. So it starts with a pool of equations that have terms that I've allowed. So things like standard arithmetic operations or trigonometric operations or powers and logs, and then it composes them in a binary tree till it can represent any equation as a tree. And then it uses each tree to try to find some kind of loss. Like it's saying, if I have this form of the equation, I can fit for the coefficients and I can find how well this equation at best can describe the system that I'm trying to model. And then it creates a family of these equations, and then it optimizes them over generations. So in each generation, there's a probability that you can have a mutation or a hybridization of two trees to create a new tree. And it will then test whether that performs better or not, and it will keep growing and shrinking the pool of equations over time until it gets a set of matches. So here, for just the overall normalization, these are sort of the sets, the most fit equations that it sustained at the end of my run. This is the same for Simba, but Simba apparently was simpler. It just was a function of halo mass and wind speed. It's like, if I have those two things, I can get you the normalization, nothing else matters. And this is Astrid. So there's this sort of different equations that hold true across the different models. And these are sort of the next step after that. So I take all of these equations and I use them as, in my head, a prior as I start out trying to write down an equation by hand that would be a superset of all of these. but be simple enough where the same equation can then apply across the three models. So instead of those 30 different equations, this is now one equation that generalizes across this set of TNGs and by an asteroid. And this is the normalization. You can now do this for all the other parameters as well. And this allows you to now get one set of equations that tells you how the shape of the star formation history changes as a function of both state variables, so that's the stuff in blue, of cosmology in green, and of these bespoke feedback parameters. So it tries to prioritize, well, I try to prioritize the state variables more than the feedback parameters because those tend to be model dependent. But the nice thing is now this set of equations fits all three models. The only thing that's different are the actual coefficients. So the form is the same, which is really interesting because I wouldn't have thought at the start of this analysis that you would be able to find a set of equations that is common. And so I went back to something dumb and I tried to see whether this makes sense. So you can use something called a random forest, which just makes a decision tree to try to fit X and Y. So it's can I predict Y based on X? X in this case is my feedback parameters. Y is the star formation rate at a certain look back time. And I can then do in these decision trees, what are the dominant factors that help you make a decision? So you can get a rough feature importance by training a random forest. And so this is just me looking at, as a function of time, which parameters are important to predicting the star formation rate at some time in the past. And the really cool thing here is that the overall qualitative shape is the same across the three models. This is why you could have a common set of equations to begin with, right? And then the actual individual importances change as a function of model, which is the different coefficients. But overall, at early times, it's just the cosmology. At intermediate times, when the sort of cosmic noon is happening, is when the halo accretion matters. And then at late times, it's a bunch of different feedback effects all coming into play. Is this true for the equations as well? So at early times, which is the rising slope, it's primarily cosmology from the omega matter that determines what the beta should be. The overall normalization depends on halo mass, so that's sort of around cosmic noon. And then the late time equations for tau and alpha tend to be the ones that contain most of the feedback parameters. So this is a useful consistency check. This was sort of as far as I got in this paper, but the fact that we now have a unified model means we can now go to other things like the Swift-Eagle model, which is quite different in how both feedback and star formation are implemented, and see if these equations still hold. You can also try forward modeling this into observational space along with selection functions to see whether you can actually now get some constraints on these coefficients, which now generalize across models. And if we can combine the earlier short timescale stuff that I talked about with the sort of longer timescale approach. So that's sort of trying to take these observations and connect them to the physics in some way. I'm not going to talk about this, but ask me if you're interested, because there's stuff that we're trying to do that can work for much larger samples of galaxies, but also on slightly longer timescales. This is stuff that I'm doing with a student in Japan who's very, very fun to work with. And the thing is, you can now flip the y-axis from number of galaxies to spatial scale. And this allows you to now start seeing all of these as physical processes that act both in space and in time, and try to construct models that account for both of those and combine the information that we have. This also allows me to put a bunch of other projects sort of on the same framework, including some future stuff that I've been working with, such as looking at how star clusters form on very small spatial scales at very high redshift. So I'm going to stop here so that we have time for discussion and questions. But yeah, these interpretable machine learning models allow you to take really complex data sets and try to do model building with them instead of just fitting for a coefficient or making a prediction. So I feel like this opens up many exciting possibilities for what you can do in the future with these suites of simulations and with the breadth of observations that we're going to get from the combination of Roman, Rubin, Euclid, and ZWST. So thank you so much for listening. Let's talk.
Great questions. We have lots of time.
Mm-hmm.
So you parameterize this automation history shape with the feedback, like timescale.
Yeah.
Have you like checked like the gas masses? So I was like curious whether is it the feedback or is it like the initial gas mass that shape this automation history?
Right. I would say that they're, so I mean the baryon fraction plots sort of have that to some extent. Let's see if I can go back. Yeah. So in this is the stellar and gas mass over the halo mass, and the bottom shows just the stellar mass. So the majority of these halos is gas, and we tried putting in the redshift 0 gas mass as a constraint, but those were less informative. So we tried a bunch of different parameters, and the ones that we finally stuck with were halo mass, baryon fraction, and black hole mass as the three most orthogonal things that we could use to describe the galaxy. But like if you do it at higher redshifts, I think the result might be different.
Yeah, this symbolic regression.
Mm-hmm.
I'd never heard about this before.
Right.
Yeah, that's cute. But I'll ask an old-fashioned question.
Yeah.
How can you then interpret the loss function?
Mm-hmm.
Is it good or bad? How do you even do, counting trials and all of that if you're allowing yourself this freedom to, choose a whole lot of shapes, right? I know how to do, likelihoods with power law expansions where, there are clear, well-defined functions. But you're not playing with a whole, space of functions.
Yes.
So how do you even decide whether it's really significant or you just lucked out with some, fortunate selection of functions?
It's a very good question. I will say at this point in, like, symbolic regression this project took 3 years to do, and in that time symbolic regression has already changed, in how it gets applied. And this sort of genetic algorithm that we are using in here does not tell you that you found a global minima.
Okay.
Right? So it could very much be that you lucked out and you found an equation, or you haven't, and this is not the best form of the equation. Which is partly why I did that third manual step of trying to construct equations by hand, using information from the symbolic regression to guide me instead of saying that that's where I stop. The second part is, like, if you are doing purely symbolic regression and you want to trust the result that comes out of that, there's a bunch of advances that have happened in recent times. So the way this works is you start with a bunch of equations, you find the best coefficients that work for each equation, and then you mutate these equations and evolve them over time as a population to see if some combination gives you better results. Every time you're fitting, the coefficients are changing with just like least squares or some Levenberg-Marquardt algorithm to find the best. But it's still discrete in the equation space. People are now trying to be continuous in the equation space by using these things called CAMs, or Kolmogorov-Arnold neural networks, which basically say that instead of a functional form, I'm going to use a set of beta splines that parameterize this sort of function that I'm regressing over, and then almost in post, as an interpretability step, it will decompose that into a function. So it's saying, like, it's the same thing we did with differential equations, where we were like, we can solve a set of things analytically, and then we're going to do series expansion, and we're going to brute force it.
Okay.
So there are neural networks that sort of do that, and there's another set of parallel advances where taking in unit or dimensionful quantities allows you to do this much better than, like allows you to get at global minima much better than taking in unitless quantities, because that puts very strict constraints on like the kinds of equations you can form. So those are the two things that people have tried to make this more robust with.
Yeah, thank you.
Yeah.
Is there like an approach which is kind of in between, so where you don't completely give up the functional form, but you still have like some idea about the physical laws that are allowed and you account for it in the Google equations? Or is it like...
Yeah, I don't think there is one yet. People I know are working like, just like in the CS world, people are working on these like graph isomorphism ways. So ways where you can compare two equations represented as graphs without having to give up on what you do with those graphs. So essentially, like if you can say whether two graphs are the same, then that allows you to cut down on a whole bunch of parameterizations that would be equivalent things. So these are graphs that like might have like different numbers of nodes and different labels on the nodes, but it's like, no, but these are effectively the same.
Yeah, really great talk, thank you very much.
Yeah.
You showed these recovery tests where there were 6 parameters, and generally recovery was very good, apart from the AGN, there's perhaps more difficulty there.
Yeah.
Is this maybe because the bulk of the galaxies in the simulation are very low mass, where we conventionally think AGN feedback is not important?
Yeah,
If you
so
restricted to high mass galaxies,
it does better.
better recovery maybe?
Yes. So this was me trying to match observations as much as possible. So the way I set this up was, if I don't have very many galaxies in a survey, so if I just like take an edge band limited survey with some signal to noise, and I sample 100 random galaxies between 10 to the 9.5 to 11.5 in stellar mass, then these are the constraints that you get. But if you, I don't know, but let me scroll all the way. Yeah. These are how things look like when you break it down by halo mass. So each horizontal row, each horizontal row is a bin in halo mass, going from 10 to the 11, which is pretty low mass galaxies, to 10 to the 14.5. And you can see that for AGN1 and AGN2 at low masses, there's almost no change. And then as black holes grow more massive, you start seeing subtle effects. It's still not very large, but it does give you slightly better constraints than nothing. This is in TNG, and then you can also do this for Simba and Asteroid, where the differences are more pronounced, and you can. Yeah, I'm still not quite sure why in TNG you don't see this effect as much. But I don't know. Like if anyone here knows, I would love to know.
Any other questions? Can I ask another one also? So you showed the difference in the indicators for high redshift versus Milky Way, like galaxies are down in the top. When you talked about the PSD.
Right. Yes.
Yeah. And so I was wondering, can you derive from that, basically, your like regulator type models, what kind of processes dominate in this high redshift galaxies versus redshift 0 Milky Way like galaxies?
This one, right? Yeah.
Yeah. So you have like the numbers, right?
Mm-hmm.
But then you also have this model for different.
Yes. So this is unfortunately like not a very realistic. These are numbers that was basically taken from Sandro's paper for what a Milky Way galaxy might have. There's 3 timescales and 2 sigmas in this model. So there's here. So what we are calling the like overall burstiness due to the dynamical part, and then the short time scale burstiness. And so when you fit this model to the observations, you'll be able to get these 2 parts. But these are like effective sigmas and effective time scales. So you essentially get like 1 long time scale, 1 intermediate, and 1 short time scale on which the power law has breaks that might indicate some physical phenomenon. What these parameters actually mean will still need some interpreting. Here we just call them like inflow, equilibrium, and GMC lifetime timescales. But like, because there's so many different processes acting, it's going to be some effective combination of. But even then, even constraining those timescales is going to be useful, because then that allows you to map back to simulations and say, do the simulations have the same timescales? Like, have a feature on those timescales.
Right. If there are no more questions, let's thank Kartheik again. And yeah, we'll resume with ITC Colloquium in late January, so everyone have nice holidays.
Yeah, have a good break, everyone.